everyone, so thank you all for coming. So yeah, today we're going to start on the topic of chemical kinetics. So we're on workshop 11. This is our first chemical kinetics workshop. And really after this kind of overall general chapter and area, you'll do a little bit of organic chemistry, and that really depends on what your professors decide to tune in on. But for the most part, the rest of your course will be chemical kinetics. So I want to make sure that we get a really good understanding of what's happening and how to interpret these type of questions. We'll go through some examples and we'll talk about reaction rate, average reaction rate, rate law, reaction order, and then just kind of determining how we can get an initial rate. So we'll go through all of this today, and we'll start off with looking at the given following chemical equation. So we have 4 equivalents of HBr reacting with O2 to give us 2 equivalents of Br2 and water. And we want to determine the rate of disappearance of HBr. We want to define it in terms of a formula, and then relate that rate to the formation of Br2 gas. So when we're looking at the rate of a disappearance of a substance, right, we're going to use our delta sign. And the delta just means we have a change. Now we're going to look at the change since we want the rate of disappearance of HBr. We'll look at delta for HBr, right? That'll be the rate of change in concentration since we have it in square brackets, right? We can see that this will be the concentration. And then we'll divide it by delta T, which is our change in time. So since our concentration of hydrobromic acid is decreasing over time, right? It's a reactant. We can see that it's a reactant. If our reaction is going in the forward direction, that means that the concentration of HBr should decrease. So since our concentration of HBr decreases over time, then we're going to, if it's going to be a rate of disappearance, we'll give it a negative value. Decreases, disappearance gets a negative value. Another way that we can kind of generalize this is to say that if we ever have reactants, our reactants in terms of our rate should have a negative value, right? So this would be, we should actually have a negative sign there to indicate that we're actually losing a concentration in the change of HBr. Okay, so now for part B, if we want to relate A, the disappearance of HBr, to the formation of Br, right? Now we need to look at something that's really important. We need to look at the stoichiometric ratio between our desired reagents. So we're comparing HBr to Br. So we need to use the ratio of HBr and Br in our chemical equation, right? And when we're looking at comparing our rate laws, we'll still look at the change in the concentration of HBr over the change in time. And because we're losing, HBr will be negative. And we want to equate it with gaining bromine. So we need the change in the concentration of Br2 over the change in time. And the last thing we want to think about is whether it's being formed or disappearing. So if it's disappearing, we'll use a negative sign. If it's being formed, we'll have a positive sign. And the last thing we want to think about is the ratio between our 2 species. So when we're looking at the ratios of formation and disappearance, we'll actually use the inverse of the stoichiometric ratio we see. So for HBr, we see that for every 4 equivalents of HBr, we get 2 equivalents of Br. So when we actually make a ratio to compare them, we'll use 1/4, right? We're taking the 4 from our HBr species, 1/4 equivalent of HBr for every half equivalent of Br, right? So that's how we'll compare the change in Br. If we wanted to summarize this, right, if we have 1/4 and 1/2, we could also say that this would be minus 1/2. You can take out 1/2, and it'll be 1/2 in the change of the concentration of HBr over the change in the concentration of time. So that'll be negative, and that can just be equal to the change in the concentration of Br over the change in time, right? So this is how we can relate species together in a chemical equation. And this is just a specific example. You can imagine that we could also include a rate relationship. So these are our rate relationships. We can include a rate relationship of HBr to water. And if we want to think about that rate relationship, then we'd have the same ratio as well, right? It would still be a fourth to a half. But now for water, we would look at the change in concentration of H2O water over the change in time. Right, any questions about that before we move on to the fun stuff?
Jade, are you writing? Because I can't see it on my screen.
I am writing. Can anyone else not see the writing?
It like froze after the delta HBr.
After here?
Like the very beginning where you just wrote the delta bracket HBr.
Oh,
like I could see you talking, but I couldn't see the rest. So I don't know. Maybe it was just me.
Let me see something. All right, so hopefully we got that problem fixed for everyone. So now let's move on to example 2, where we want to actually calculate a rate of disappearance. So for our rate of disappearance, you have to be, for most of our kinetic information, sorry, for our kinetic calculations, you have to be given lots of information in order to be able to make any calculations at all. Thank you. So what we're looking at is now we have a different equation where we're taking N2O5 and generating NO2 and O2. And with this reaction, we're given specific reaction conditions. So we can consider a time of 500 seconds to have a certain concentration of N2O5. And then at 1,000 seconds, we have a different concentration of N2O5. So we're just saying that as time proceeds, our concentrations of reactants and products are changing. That's all these trials are telling us. And we can use this information to determine a rate. So if we want the change in the concentration of N2O5, right, over time, then what we need to do is actually take these values, and we can take our values of concentration, right? So our change just means that we want to take one value minus another. Oftentimes we want to pick, in terms of our time, we want our time unit to be positive. So it doesn't matter what our concentration is. We just want to make sure that we arrange our trial so that the time unit is positive, right? So in terms of time, we'll take 1,000 seconds and subtract 500 seconds. And we need to keep our concentrations in the same order. So since for 1,000 seconds, we had a concentration of 0.93 times 10 to the minus 2, we'll make sure that that's the concentration that we write first. And then we'll subtract the concentration of our second time point, which is 1.24 times 10 to the minus 2, right? So we'll answer that equation, and then our final answer should be negative 6.2 times 10 to the minus 6, and then our unit should be in molars, right? Our unit should be in molar per second, because when we look at our calculation, the concentrations in the numerator are in units of molar, and in the denominator, our units are in second. So molarity per second. So this would be the rate of disappearance of N2O5. If we wanted the rate of formation, of NO2, we can actually use the information that we have from the rate of the disappearance of N2O5 to figure that out, right? So now what we want to do is use our formula for N2O5. So we know that for our change in the concentration of N2O5, we'll divide that by the change in time. And we can see from our balanced chemical equation that for every 2 equivalents of N2O5, we have 4 equivalents of NO2. So we'll use the ratio of a half here, and it should be negative because that's disappearing. And that will be equal to the change in concentration of NO2 over the change in time. And since we're creating NO2, this will have a positive value, and the ratio there will be 1 over 4. Based on the stoichiometric values of 2 and 4 that we see here, we can take them to our rate relationships. So now that we have these rate relationships, we can take the concentration of NO2, and we're saying that a negative half of the concentration of N2O5 is equal to a fourth of the concentration of, a fourth of the change in concentration of NO2. And when we do this calculation, really what we're saying is that we can take negative 2, multiply it by negative 2, and multiply it by negative 6.2 times 10 to the negative 6 molar per second. And this gives us a concentration of 1.24 times 10 to the minus 5 molarity per second. Right, so that would be our rate of formation of NO2 compared to N2O5. Now if we want the rate of formation of O2 compared to NO2, let's see if we can set up that equation. Right, so now what we want to do is we'll still say that for a half equivalent of the change in concentration of N2O5 over the change in time, now we want to look at the stoichiometric ratio when we compare it to O2. So for O2, we see that the value is just 1. We can still write 1 over 1. Technically, that number will always be 1. And then now we'll look at the concentration of the change in concentration, of O2 over the change in time. And we want to set those equal to one another. And when we do this equation, really what we're saying is that we need half of our value for N2O5 to be equal to the value of the change in concentration for N2O5 to be equal to the change in concentration of O2. And we also need to change the sign. So this value would be 3.1 times 10 to the minus 6 molarity per second. Okay, cool. So we've kind of looked at every part of our reaction. And now what we want to think about is what is our average rate of our reaction? So we can get our average rate of our reaction by looking at the rates that were given and actually just taking the average. So if we combine all of these rates together, right, we can add the rate for the reaction of C, in part A, part B, and part C. And when we get the average, a simple average, add them all together, divide by 3, we'll see that the average rate of our reaction is 3.1 times 10 to the minus 6 molarity per second. Right? So that would be the average